Alright, time for another DraftPhysics.com, DebatePhysics.com, also video presentation. Alright, so again, on the subject of charge, and we're using the Wikipedia page as a starting point, and disappointingly, okay, their page on charge is really thin, okay, in terms of material, or much to care about. And yeah, I'll read part of this history. I mean, the early history is just, not very good. So all the way up to Franklin, it's kind of just, okay, they noticed this thing with amber, and they noticed this thing, you could make a spark here and there using different things, but not much was stated until Franklin basically created all the vocabulary and the assignment, basically, of the idea that this all can be explained not as two different charges, but as just the, more of one than the other, more of something. And so the idea is basically, instead of wasting time talking about all the mistakes of the past impressions, we sort of know that the nucleus is net positive. Now, I would argue that the neutron is really a dipole, the smallest one. It's an electron and a proton, and it's very close together. And so what you're really just saying is that you're creating a nucleus that basically is going to have another proton, a stick to that neutron, to, in a sense, balance its two sides. And that explains the net positive of the nucleus. So they're very close, electrons and protons, very close together in the nucleus, and the exterior electrons are just trying to find a place where they are balanced between the electrons and the protons. They have to find a place where they're not too close to an electron, and they can get closer to a proton. And the idea is the protons are essentially protected by electrons in the nucleus in certain locations, and so electrons can't join the nucleus. They have to stay at some distance from the nucleus. Those are the electrons that are part of that are hard to move. And then you can have other electrons, free electrons essentially, that can just still see the positive nucleus, and they're, they can be associated with a surface, and they have to be propelled by some sort of energy to force them off of that surface, because they can see the positive. So until you bring another nucleus somewhere near them, they're not going anywhere, because they're in a position where they see more positive in one direction than they see in another. They're just looking for positives, and the only thing that gets in their way are negative charges, the thing they're repelled by. So it sort of explains why the charge will pile up, even though the electrons don't like each other, is because it still just depends on where the closest proton is. All right. And so what all you're really doing is saying the protons don't move, the electrons do. So you can always change the amount of electrons on a surface, but you can't change the amount of protons. Okay. All right. So it is known that Franklin's model was fundamentally correct, that there is only one kind of electric charge. So I would say that's a mistake to make, is that all you're doing is saying, okay, yes, all you can regulate is how much of the electron or negative charge you can control. But obviously, when you're controlling it, you're controlling how positive the positive looks. So it's obviously not just one. Anyway, and only one variable is required to keep track of the amount of charge, and the variable is how much compensating. So you have a net positive nucleus. All the nucleuses are net positive. And you're just saying if the number of electrons doesn't compensate for that net positive, then the net positive is still pretty strong. Okay, until 1800, it was only possible to study conduction of electricity by using an electrostatic discharge. So now they're just going to get into the battery stuff. In 1800s, Alessio Volta was the first to show that charge could be maintained in continuous motion through a closed path. So Now charge moving, so this is just, again, it's just electrons. So now you're just saying I can move electrons from one place to another if I have a conductor. But they won't move unless I have a conductor. So that's the interesting part, that there's a resistance to movement, like from empty space. So there's no compulsion to move, again, until you introduce a positive charge somewhere that the electron can see. And if there's not a positive charge it can see somewhere, it'll stay where it is. In 1833, Michael Faraday sought to remove any doubt that electricity is identical regardless of the source by which it is produced. Okay, well, that's not too interesting, but yes, they were doing eels and all kinds of different kinds of electricity and had some impression that maybe these were different forms of electricity. He discussed a variety of known forms, which he characterized as common electricity. Okay, so magnetic induction, static, and piezoelectric. Voltaic electricity. So this is getting, they're jumping through really, important decades of where lots of people were doing lots of experiments with electricity. In 1833, Faraday raised the question about whether electricity was a fluid or fluids are a property of matter. And I don't even think Benjamin Franklin thought it was an actual fluid. I think what he was saying was it flows like a fluid. And what you could imagine someone speculating is that the fluid is sand. Sand can flow like a liquid, but it's made out of little particles. And so the idea of it flowing is the only part they should have thought about instead of using words like fluid. Like gravity, he investigated whether matter could be charged with one kind of charge independently of the other. He came to the conclusion that electric charge is a relation between two or more bodies because he could not charge one body without having an opposite charge in another body. So again, that's already something Franklin was basically saying, is there's a certain amount of this fluid and you can move the fluid around. So you can take the sand and put some extra sand someplace else. And so we're just moving the negative charge because the positive charges are locked in nucleuses. You can't get them out of the nucleus. All right. In 1838, Faraday also put forth a theoretical explanation for electric charge. Faraday had lots of ideas, by the way, so there's a sort of annoying that sometimes they just highlight the ones that were right and they don't point out all the misses, while expressing neutrality about whether it originates from one, two, or no fluids. Okay, so he focused on the idea that the normal state of particles is to be non-polarized. So that he's talking about big particles now. And that when polarized, they seek to return to their natural non-polarized state. So I would argue that obviously electrons and protons are the only thing polarized in the sense that they are independent monopoles. And when they're stuck together, they're going to create a dipole, which I would argue the neutron is. In developing a field theory approach to electrodynamics, starting in the mid-1850s, James Clerk Maxwell stops considering electric charge as a special substance that accumulates in objects. So we're really jumping now, 1850, and starts to understand electric charge as a consequence of transformation of energy in the field. So the argument of fields is in electrons, right? That's the little tiny stuff that's making something, an electron or a proton. That field stuff is much more, is the stuff moving the speed of light. There's no field of electrons, and there's no field of protons. There's a field of some kind of force, okay, that affects electrons and protons and gives them their character. And so that's the part where they're just missing entirely. This pre-quantum understanding considered the magnitude of electric charge to be a continuous quantity even at the microscopic level. So we know that charge is just electrons. So this is where they're starting to mess with electricity and magnetism, which are what the electrons and protons, how they're arranged. So it's how their pattern, the pattern they create, okay, that's creating electricity and magnetism, not these things themselves. Electrons don't go somewhere to make magnetism, and electrons don't go somewhere in the sense of to change a field, an electric field. It's just the fact that when you do move an electron, you change the pattern that the world sees. You change what something looks like. All right, it looks different because you've moved electrons and protons in terms of whether it's repulsive or attractive to you as an electron or a proton. Again, the small universe is the only universe, and I'd say Maxwell's understanding was fundamentally flawed. There's nothing wrong with his math, but his understanding is flawed. And certainly to say there's no magnetic monopoles, I'd say was silly, just because we know the magnetic effect is completely controlled also by the migration of electrons. All right, so the rest of this is very, I don't see how it really relates to anything. So it says the role of charge in static electricity, and it basically just says nothing here. Static electricity refers to electric charge of an object and is related to electrostatic discharge. Well, gee, isn't that interesting? When two objects are brought together that are not in equilibrium, an electrostatic discharge creates a charge in a change in the charge of each of the two objects. So obviously, as you bring an electron towards a surface that has electrons, the electron will push on the other electrons and change the shape of the atom. It can turn the atom, it can press in on the atom, it can distort the atom, but it's going to change how the atom is functioning, and that's going to change the atom's look or polarity. So the force effects versus the actual objects is the trick here, and the point, I guess the important point to make is that these things are just radiating, the electron and the proton, and it's the radiation that creates the repulsion. So without the radiation, there's no attraction and no repulsion. The field of energy is going to decide, the state, and also is certainly going to decide whether they move or not. All right, this electrification by sliding is really uninteresting. Okay, so this is just about how you take electrons off or deposit electrons, and that really just has to do with the nature of the atoms that you're sliding across each other. If they're rough, or it's like talking about sandpaper versus, I don't know, glue. So obviously one thing will take stuff off, the other one will collect stuff, depending on how you rub them, sawtooth against sawtooth, or you could mix and match. All right, so we'll probably have to go to this electric current page, just because the rest of this is almost nothing. There's just nothing to this page, which is very surprising. Charge is the elemental function that creates electricity and magnetism, and they barely get into it at all here. There's no even, there's only a picture of a Coulomb experimental device. They don't even talk about him. So it is kind of surprising how little there is here. So let's do electric current really quick. Electric current is the flow of electric charge through an object. So we're talking about the flow of charges, which are electrons. The most common charge carriers are the positively charged proton. So we know that the charge carrier, the proton's not moving, so it's not carrying. It would be kind of wrong to say it's carrying. It just happens to be charged, but it doesn't do any of this carrying of force. And the negatively charged electron, the movement of any of these charged particles constitutes an electric current. So we know the protons aren't moving. You're not breaking the nucleuses. You're not shooting a proton into another proton into another proton. That you're just migrating loosely attached electrons, and that's all you're doing across or through a medium. You need free electrons. In many situations, it suffices to speak of Let's see, conventional current without regard to whether it is carried by positive charges moving in one direction or the conventional direction of the conventional current by the negative charges moving in the opposite direction. So this is sort of like they're saying, well, we can get away with completely distorting and misrepresenting what we know actually happens. Why would you do that? Why would you pretend that it's positive charges moving when you know the positive charges are locked inside the nucleuses and they're not going anywhere? You're not banging, neutrons into neutrons. You're not banging protons into protons. You're banging electrons into electrons. This microscopic viewpoint is an approximation that simplifies electromagnetic concepts and calculations. So they're saying it's some sort of convenient shorthand, but it really isn't right and it isn't correct. So why do it? Why pretend it's something other than what you already know it to be, which is you have to move electrons. And just move them. That's all you have to do is push them into something. Okay, so you can do the back and forth thing, and it's the same as, pushing them in one direction, because it's just about the pressure you apply to a surface. It's about whether you're applying pressure to a system of electrons. All right, at the opposite extreme, if one looks at the microscopic situation, one sees that there are many ways of carrying an electric current, including the flow of electrons. I think that's it. The flow of electron holes, so that's just crap, that act like positive particles. So there's no holes, there's just the fact that there's less electrons to compensate for the protons, and the holes only represent the fact that maybe you can use an ion and you can attach something to that atom easier because it's ionized, but it doesn't have anything to do with it, strictly speaking, a hole. And both negative and positive particles, ions, and other charged particles flowing in opposite directions in an electrolytic solution are a plasma. So again, it's just deceptive. You're just saying you're either below compensating for you either have less electrons than protons, or you have more electrons than protons, but there's no other circumstance. And you only control whether there's more or less electrons by taking electrons away. You can't add protons and subtract protons. So it just really should be made very clear. The protons are inaccessible. Beware that in common and important case of metallic wires, the direction of the conventional current is opposite to the drift velocity. So there is no such thing as drift velocity. That's just a made-up idiocy where they pretend that when electricity is going through a wire, it's moving every single electron in the wire, when the argument could easily be made that only a few atoms in the wire are involved in the transmission of the electrons. That not every single electron is pushed, only a certain few are pushed. And that's the difference between voltage and amperage. Amperage is involving a lot of atoms with a little bit of pressure, and voltage is affecting very few atoms with a very high pressure. So there's lots of ways to illustrate that, which probably will be important. Of the actual charge carriers, i.e. the electrons. So again, they both carry charge. The electrons are the only thing you can add and subtract. This is the source of confusion for beginners. Well, I'd say your experts are really quite confused regarding the truth. All right, the fact that charge is conserved isn't really very interesting. Yes, of course, you can't destroy electrons, and so you can only put them someplace else. So if you take them from one place, you have less there, and you put them someplace else, then you have more there, and it's always conserved. So that's not very interesting. And then they get into relativistic invariance, which is just absolute shit. I mean, why would you do that to this article? So they always have to throw in this relativity crap. They always have to break every subject with this nonsense. It is just that. All right, so we will move on. to electric current, I guess. We'll just click on the buttons and see where they take us. All right, I'm back. So I was just thinking, probably be worth doing a little bit of drawing here. So I will do that. Atoms are what's conveying electricity in, I think in a rational way to look at it. That's what's happening. And, it's just electrons jumping from place to place. So I would argue that inside a nucleus, this stuff is really close together. Okay, electrons and protons are really close. And again, the neutron is just the electron and proton very close together. Once it's inside the nucleus, there's very little distance between these things. And obviously the strong force is just the fact that you stick an electron between two protons and the protons can't see each other, so there's no strong force. Now the trick is that this is a three-dimensional object or a two-dimensional object. So the argument is that atoms can come in, they can come in shapes. An atom can be, shaped like that, or an atom could be a sphere, depending on where things are located. It could be a three-dimensional object or a two-dimensional object. You can sort of approximate that, and then all the crystal kind of stuff, there's very flat layers, so the atoms probably are longer than they are thick, kind of thing. The way the electrons and the protons are spread out. So the point is that the balance is created by the location of the outer electrons, that are further away because they have the repulsive influence of another electron being in the mix. So they're attracted to the protons, attracted. I don't know how to draw attracted. We'll do that with a bent line. So they're attracted to the protons, but they're repelled by the electrons. So they have to find a position where those two forces end up being balanced, and that's why everything's kind of in a jittery position. And there's only, like I said, suns only make 100 varieties of this. And so there's only 100 varieties of this geometry that is stable enough to form a nucleus that survives outside of the high pressure of a sun. So it's really tight, really close together. So anyway, so you have a net positive here, and then you have these electrons that are balancing that, and some of them are pretty far away. So they're seeing the proton, and there's only a little bit of electron in their way, so they're still sticking, but they're very loose because they're very far away from the proton. It's not a very strong attraction. So, obviously they can be pushed around really easily. And those are the electrons you acquire through charge. So you could say that stuff that charge doesn't stick to means that its surface is very like glass. It's an insulator. So you could argue that its surface has the electrons and protons are pretty close to each other, and that's why when a charge is applied, it can't migrate. It can't pass from atom to atom, as the atoms are tight, and the electrons, there's no room for the free ones. And so they're separated, and frankly you can't push them along, so it's not a very good conductor. Where like the metals with a bunch of crystals layered on top of each other, there's lots of places for the electricity to flow through the loose electrons that would be between the crystals. Alright, something like that. It's hard to go into all the details. And there's about, for each of these subjects, there's about 100 experiments that you could point to that give you a fact. Like if you want to describe a photon, there's lots of different experiments that tell you something about how photons work. And there's a bunch of experiments that tell you about how electrons work. And it's going through all of that, to find. All right, back. A lot of distractions today. Anyway, so electric current. Alright, so it says an electric current is a flow of charged particles. So they should have just left it at that, and everything would have been okay, but they're going to call ions a particle, which is just messes up the whole subject, right? Because we're trying to say, look, particle should mean something, like it's a thing that you can't break into something else, and then call the other stuff that's not particles, call them things or objects or something, but don't call them particles because they're not really a particle. All right, such as electrons or ions. So the flow of ions, you're talking about moving whole atoms. Obviously, that's not really electricity because, frankly, it would be pretty intensive in the terms of a lot of momentum. You need a lot of energy just to move the atoms. So it's certainly not going to move anywhere near the speed of light. It's going to be a lot different than electricity. All right, moving through an electrical conductor. So I don't think there's any conductor that moves ions. It moves electrons, and the movement of the electrons creates ions, but it doesn't, the ions aren't moving. It is defined as the net rate of flow of electric charge. So again, we shouldn't say electric charge, because the only thing flowing are the electrons through a surface. And its surfaces are, the moving particles are called charge carriers. So, it's again, force carrier is a reasonable concept in terms of understanding that when an electron or proton is moving, that it's carrying force because force has to push it. So that makes sense. But charge carrier, they obviously always have charge. They're not carrying charge. And so what they have is momentum. So they're, again, carrying momentum when they're moving. And that's, so they're force carriers. They aren't charge carriers, which may be one of several types of particles. So this is, again, more nonsense about, that there's more particles than just electrons and protons. No, there isn't. And the only ones involved in the electric function is the movement of electrons, depending on the conductor. So again, what's the point of talking about conductors that aren't really conductors? Okay. Plasma, like for example, is not a conductor. It's a bunch of atoms, all right, that are basically hot. Okay. So you're moving atoms. That's heat when you move atoms. When you're moving just electrons, that's not heat. All right, in electric circuits, the charge carriers are often electrons, so they're always electrons. It should pretty much be stated. Moving through a wire. In semiconductors, they can be electrons or holes, so theoretically, there's no such thing as a hole. You're just saying there's an absence of electrons, which means there is a place for electrons to stay if you provide some. The holes are just the absence of electrons. It's not a hole. It's a place where the proton is visible. Any place a proton is visible, you could just sort of understand that if there's an electron somewhere and it sees, so the electron's blue, let's say, and the proton's red. If the electron sees red somewhere, it means it's going to end up being pushed there. All right, an electrolyte, the charge carriers are ions. So again, they're not really charge carriers. They're atoms moving, and they're ionized in the sense they either lack an electron or they have too many electrons, and they end up going someplace, and when they stick to that place, then they deposit either their extra electron or they create a surface that has an inefficiency of electrons. While in plasma and ionized gas, they are ions and electrons. So I think it just messes up the subject of electricity to talk in any other terms but what you're doing with moving electrons. And the consequence of moving electrons can be the creation of ions, but the ions aren't what's being moved. All right. I mean, you really wouldn't call plasma electricity. It's a little different. All right, an international system of units, electric current expressed in units of amperes, which is equivalent to a coulomb per second. Ampere is the SI base unit. Okay, who cares? We get that. There's voltage and there's amps. All right. Electric currents create magnetic force. So they're not creating anything. They're just changing what exists. So again, they're just doing this. They're just turning something that looks red into something that looks blue. That's all they're doing. They're just changing the pattern that the surface is creating. That's it. It's either a very blue pattern or a very red pattern. And it's just where the mixture is decides whether it's a pattern you would call magnetic, in the sense that it creates a pattern that's polarized. Polarized would be, well, the bullseye argument, where you have a bullseye with the blue in the middle and then a red and then a blue and then a red, or a red in the middle and a blue and then a red. And those two things, although very identical in some respects, are, that's the opposite magnetic charge sense. That's what that allows those two things to see each other and be pushed into each other, where if they both have red centers, they can't be pushed into each other, they repel. So that's the north-south, is just a phenomenon of the arrangement of the charges, the pattern it creates, and you match the patterns. So something that is likewise capable of seeing a bullseye, in the sense that it has a bullseye detector, it can see the magnetic field, because the magnetic field is just a pattern. Jeez. So they imply the existence of a force being created. It's not creating a force, it's taking the force that already exists and giving it a shape, a pattern that other things that are polarized can see, but things that aren't polarized can't see. All right, symbol, who cares? All right, conventions. The conventional direction of current. So this is the big problem here too. So we know that the electrons are flowing in a direction. We know the voltage is the pushing pressure of the electrons. And we know that the amperage is basically the number of electrons. So you can do two things. You can move an electron quickly, or you can move a lot of electrons slower, would be kind of the better analogy. And they're going in the same direction. There is no difference in their direction. So it's just wrong to say amps move in a different direction than voltage does. It's just wrong. It just makes a mess of the subject, frankly. Also known as conventional current is arbitrarily, so again, it's not arbitrary, it clearly has a direction. There's no point in saying somehow direction is arbitrary, because it's not. Defined as the direction in which positive charges flow. So there are no positive charges flowing, so again, it's just wrong. So they're just saying by convention they're going to pretend amps are going in a different direction than voltage, and it can't, it's not. In a conductive material, the moving charged particles that constitute the electric current are called charge carriers. So again, they're not carrying charge. They are charged, and what they're carrying is momentum. That's why they can do work, is because they're carrying momentum. All right, in metals, which make up the wires and other conductors in most electrical circuits, the positively charged atomic nuclei of the atoms are held in a fixed position. Right, so why are we talking about moving them? And the negative charged electrons are the charge carriers. So again, it's just wrong. They're force carriers, not charge carriers. They are charged. I mean, this is just such a mess of language. They're just ruining vocabulary here. It just doesn't... it's just wrong. Free to move about in the metal. So again, there are electrons that are associated because they can still sense protons, all right, but they're loosely held rather than strongly held. There's a lot of pressure from other electrons telling them they can't stay here, and so they're in a balance that's net positive, so they stay, but that's it. They still need to go somewhere. They still need a net positive thing to go towards. They can't be propelled merely by negatives, because the negative will just push them out further. It won't give them a velocity. In other materials, notably semiconductors, the charge carrier can be positive or negative. So it's obviously there's no nuclear portions moving, depending on the dopant used. So again, they're still just talking about a relative difference in its amount of electrons. So less electrons versus more electrons. Positive and negative charge carriers may even be present at the same time. So Who even wants to think about what they're talking about there? As happens in electrolyte in an electrochemical cell. All right. So just really, I say, very bad way to describe the mechanics of electricity, which is really just electrons pushing on other electrons, pushing on other electrons, pushing on other electrons. All right, the flow of positive charges, see, more nonsense, gives the same electric current as and has the same effect in a circuit. So there's no flow of positive charges. So why are they saying that? The positive charges don't flow. You don't flow. You don't push. You don't move protons. You're not pushing proton to proton to proton. You're only saying less electrons versus more electrons. All right. As an equal flow of negative charges in the opposite direction. Since current can be the flow in either positive or negative charges, since current can be the flow of either positive or negative charges, it really can't be. So why are they saying that? Why are they saying directly here that there's a positive charge moving when there's no positive charges ever moving? You're either just extracting electrons or adding electrons. It's either too few electrons or too many electrons. There's nothing in between. There's nothing else happening. That's what Franklin, they write it right up there that Franklin was correct, that the whole system runs on just one quantity. And there's either too little of that quantity or too much of that quantity. There's no other quantity. All right. Are both. So that's just so wrong. A convention is needed for the direction of current that is independent of the type of charge carriers. Whatever that even means. You need a convention? I don't think you do. Negatively charged carriers such as electrons, so that's the only carrier there is, and it's a force carrier, not a charge carrier. It's a momentum carrier, not even a force. It's carrying force in the sense that you can't move an electron unless something's pushing it. The charge carriers in metal wires and many other electronic circuit components. Therefore, the flow in the opposite direction of conventional current flow in an electric circuit. So again, just makes no sense. They flow in the same direction. It's just a physical fact that the one thing is just about volume and the other thing's about speed or pressure. And that's it. Voltage you could associate with velocity, and amperage you could associate with volume. It's how much water and how much pressure it's under. A current, the water analogy is a very good analogy. A current in a wire or circuit element can flow in either of two directions. Well, that's duh. But what's flowing is either too many electrons are going that way or too many electrons are going that way. All right, when defining a variable I to represent the current, the direction representing positive current must be specified. So again, there's no positive current, usually by an arrow on the circuit schematic diagram. You're just saying the place that has more electrons, okay, is in fact going to be the place that's going to be called negative, and the place where the electrons were extracted from is going to be called positive. This is called the reference direction of the current I. So again, it's always relative. You can have, you could have 5 volts, and relative to 10 volts, 5 volts is minus 5 volts. But it's really not minus. It's only negative relative to a positive. When analyzing electrical circuits, the actual direction of current through a specific circuit element is usually unknown until the analysis is completed. Who knows what they're talking about there? Consequently, the reference direction of circuits is often assigned arbitrarily. It's hard to imagine writing up a circuit and not knowing which way the electricity is flowing, but whatever. When the circuit is solved, the negative value for the current implies the actual direction of current through that circuit element as opposed to that chosen reference direction. So again, we know the actual current is going in the same direction as the voltage, so I don't even know what they're talking about. All right, I don't know if Ohm's law is all that interesting, so we'll skip over that. I mean, it's nice that there's this clear relationship between the watts, the amps, and the volts, and that's all really good stuff to know. And so I just don't know if there's much else to glean out of it. I mean, how much resistance the voltage has will decide how much current there is. Okay, you know, lots of these things make perfectly good sense. So I don't know if that's really interesting. I mean, interesting in what sense, right? Yeah, because it's always interesting in the sense that why would there be any resistance to the flow of the electricity, and the fact that there's kind of an intrinsic resistance in the sense that there's always some limitation to how much electricity you can put through a wire. Even when it's a superconductor, there's still a limitation. You can't put an infinite amount of electricity through it. But it's much more, it doesn't create heat, which is the benefit. So you're not wasting any of the force pushing stuff that isn't going in the direction you want it to go. So you're basically just taking all the noise out of the motion of the electrons. None of them are moving in the wrong direction. All right, none of them are bouncing backwards, that kind of stuff. So resistance is really just talking about an impurity or a defect in the capacity of the current to allow the stream to flow. So it's like sticking impediments in the way that just slow it down by stealing some of the energy. So resistance is clearly associated with how much you're losing to heat. All right. Yeah, that's probably good enough. So we'll do alternating and direct current. So all this really means is constant current versus current that isn't constant, that stops and starts. And that stopping and starting, okay, induces creates effects that can transmit the pattern to other conductors. In alternating current AC systems, the movement of electric charge periodically reverses direction. So you don't need to reverse direction to cause induction. So that should be understood. AC is in the form of electric power, most commonly delivered to businesses and residents. It's usually waveform of an AC power circuit is a sine wave. So again, this waveform stuff is really, again, kind of irrelevant. You're really just talking about how you get from your peak to your valley to your peak to your valley, and you could logically understand why there would be certain advantages to doing that proportionally. Through certain applications, use alternative waveforms such as triangular and square waves. Audio radio signals carried on electrical wires are also examples of alternating current. An important goal in these applications is recovery of information encoded, okay, on the signal. So you can do that with the AM, changing how loud the signal is, or you can change it by changing a whole range of frequencies. All right, in contrast, direct current refers to a system in which the movement of electric charge is only in one direction. So again, direct current has to be a constant current, because as soon as you turn it into a periodic current, then it's going to behave essentially like an AC system. Direct current is produced by sources such as batteries, thermocouple solar cells, and commutator-type electric machines of the dynamo type. Alternating current can also be converted into direct current through the use of a rectifier. So that's just using diodes to basically, what's the way I could say it? It's just to adjust the phase. Put the phases on top of each other. Put half the electricity on top of the other half of the electricity. So when one side's down, the other side pops up. So you're just essentially slowing down one side, slowing down half the electricity so the two phases match. Well, they don't match. They're exact opposites. Direct current may flow in a conductor such as a wire, but can also flow through semiconductors, insulators, or even through a vacuum, as in electron or ion beams. So obviously that flow, okay, so is without a conductor, and the point would be is that that flow it is encountering resistance. So so there's a whole theory to how you can, by creating a positive and you have a negative, and you take a vacuum and shoot electrons. Now that's the funny part, right? Because the vacuum is supposed to be an insulator. So it's, you have to say, what you're doing is you're actually have to propel the electrons at a pretty high velocity because you're not using any conductor. So you know that the electrons have to be pushed aggressively if they're going to be able to be transferred. So even, lightning bolts need to create atoms. They need a row of atoms to travel through. Ions. So, well, that's one of those things where you have to start talking about, well, why is it that electrons will jump? And the reason why they will jump is because they can see a positive. So again, if you can create another positive that's strong enough, the electron will fly there on its own without having any atoms to use to just bump electrons. But in all the other cases where you're not giving them that much energy, they need atoms to be able to just push on weakly bound electrons. So if you're going to try to jump the gap, you need a lot of propellant to allow an electron to jump the gap. Something like that. All right, so maybe we'll call this a video. Yeah, it might be enough. And then we'll move on and on and on and on. But I mean, really, to talk about electricity as if it's something other than just the idea of moving electrons from one place to another place, and that's the electricity part. And it really isn't about moving atoms and moving a whole bunch of other stuff. It's really just about moving electrons. And yes, atoms can carry an extra electron, or they can carry less than a deficit in electrons. But the charge and the electricity is really all going to be dependent on moving electrons. All right. So till the next time and such, so forth and whatnot.